Hello and welcome to the last webinar of our series, Simple and Accurate with Allplan Bridge. Today we will talk about traffic load analysis. My name is Dieter Wagner. I'm a consultant at the Allplan Infrastructure Competence Center in Graz. And I would like to show you in the next about 30 minutes, maybe some minutes longer, how to introduce traffic load analysis in Allplan Bridge. I will give you a short introduction about the principles and backgrounds, how the analysis is implemented in Allplan Bridge. And in the second part of my presentation, I will give you a short live demo so that you can see how it's directly done in the software. The traffic load analysis itself, it's a bit, I would not say difficult, but a bit more complex than a normal load case calculation, like wind load or temperature or whatever, where we can put all the information directly in one load case. So for the traffic, it's a bit more complex because, you know, we have the particular lanes, we have particular load trains, and we need to evaluate them and find out the most unfavorable positions of the trains. And in Allplan Bridge, this is implemented on the basis of influence lines. This I will explain now in detail. So first of all, I will give you an overview of the whole concept. And in the following, I will then go more into detail for all the particular points. So the first point would be to define the lanes. So I think most of the design codes have a similar approach so that you have a certain distribution of lanes on your surface, on your roadway. And in Allplan Bridge, we can apply this in a very same way. As I said, just details are coming up in a minute, just to get the overview first. The second step would be the definition of the load trains. So also here we have possibilities to define any arbitrary load train that we might have. Details also in a minute. And finally, based on the defined lanes, or rather the load positions. So you see the lane, of course, it has a certain width, and here in the center, usually per default in the center, there is the load position. And for this position along the structure, we evaluate the influence lines, so to find out the most unfavorable position of the load in longitudinal direction. Then in the next step, we are evaluating a certain influence line with a certain load train, like this load train here might be positioned here, and the results of this calculation are stored in an envelope. So this envelope contains then the maximum and minimum forces and displacements of this particular result, which means at the end of the calculation, we will have a lot of particular results from different trains on different positions. And so we have one final step where we superpose these individual results to a final envelope. And this works exactly the same way that you also already know from other loads like settlement or temperature or wind loads. It's the same scheme, the same principle, and it will result in a final envelope, which we can then use in our combination table. We can factorize it, of course, respectively, and use it then for the design code checks. Yes, that's the principle. And now let's have a closer look at the particular points of this workflow. We will start with the lane definition. As already mentioned, our approach is pretty much the same as you also get it from the code. So the code prescribes a certain width of the lanes, and in the same way, we can apply the lanes in Allplan Bridge. And the nice thing about it is we can really apply it on the real cross-section. So it's not just a scheme, but you're really putting the lanes on the cross-section of your model. And we have a generic approach for this. So you can arbitrarily define the lanes as you want, or in terms of Eurocode or AASHTO, we can also automatically distribute the lanes according to the code. So there's just a tool that will, where you just define the width of the roadway, and then also this definition of the lanes is done automatically. And then when we define those lanes, we can tell the program for which direction we want to evaluate the influence lines. So usually you will have the vertical direction, but could also be that you want to investigate in this centrifugal load, or maybe also in some braking force in longitudinal direction if you want to evaluate this also on the basis of influence lines. Moreover, there is a combined way for defining the vector. Like you say, you have maybe some vertical load, 100%, and you have maybe a 10% centrifugal load. Then you can define here a vector with the intensity of 1 in the vertical direction and 0.1 in the centrifugal one, which means then you have one resulting slightly inclined direction defined at once. We can also define more load positions on one lane, but that's actually not related to wheel loads. So as you know, at the moment, our analysis is based on beam theory. So in fact, it really doesn't matter if we calculate wheel loads or if we have the resulting load, because everything will be referred to the center of gravity of the beam model. So this just means that I can investigate different load positions, so different influence lines on the same lane if I want to do that. Okay, the second point would be the definition of the load trains. Also here we have a generic approach, so you can define any arbitrary combination of single loads and uniformly distributed loads. So you can see this here in this picture. So I have here some concentrated single loads and some uniform loads. And the uniform loads can be like line loads, as for example seen here, kilonewton per meter. But you can also define area loads like in kilonewton per square meter. If you do this, then it's nice. Then the program will automatically multiply the area load by the width of the lane. And this also works if you have a changing lane width. So which means if the remaining area, the width of the remaining area is changing, you will always have the accurate line load on it. Between the loads, we can have some distances. So the distance can be constant, like seen here, for example, or it can be varying between two values, 3.5 and 12 meters in this case. So of course, it's just an example. And the loads themselves, the uniform loads, they can also have a fixed length, like you can see here, 5 meters, or they can also change between a certain interval, let's say between 1 and 6 meters for this load. And probably the most useful case, they can be like infinite. That means the program will evaluate the most unfavorable length of this load to be applied. And if necessary, it will also be split into several parts, which I can show you then also in the program. That's about the load definition. So the next thing would be the influence lines. Actually, you will see when we then do this superposition, the user doesn't really need to take care of the influence line calculation that's done in the background. So this is just I will also show in the program some preview, some animation, how this works. So for each position along the structure, so for each element, I get the most unfavorable results for all the internal forces and all the displacements. And on the basis of this, we can then evaluate a certain load train to get the real forces. The final step would be the evaluation. So we have now defined the lanes and we have defined the trains. And now first we want to evaluate a certain train on a certain lane. And then we want to superpose them to a final envelope. Maybe I just jump a bit back before I explain this. So as I said, we have now, let's just stick to the Eurocode, for example, where we have these tandem systems. So I want to also in my demo, I want to show you how to apply the tandem system. And now, of course, you know this lane number 1, which is, let's say, the heaviest lane with the heaviest tandem system. It can be placed on any position here, and also the second one. So the distribution of the lanes could be in an arbitrary combination. And so, of course, this would result in a lot of calculation and a long calculation time. So due to this, we do not do this fully automatically, but the engineer must think a bit of how the most unfavorable effect could be placed or should be placed for the transversal direction, right? And as I mentioned before, as we are in beam theory, actually for the bending moment and for the shear forces, the distribution in the transversal direction doesn't matter at all, because it will always relate to the beam axis, so it doesn't matter where this vertical load is positioned. But of course, for the torsional moment, we have two extreme situations. So one is, if I say it's anti-clockwise, so I will start with the heaviest strain here at the outer lane and put the second heaviest strain here, and so on. And for the other side, for the right side, for the clockwise torsional moment, of course, I will start with the heaviest on the right and going to the left. And these are actually the two positions I need to consider. And finally, I will then superpose them with or. So of course, they will not happen at the same time. So I say either the most unfavorable effect comes from the one situation or from the other. And so just to understand the next layout that we are going to show here. So when I do this superposition, first of all, what I will do is the evaluation of the load trains. So I'm here in this interactive input scheme. We will also see this then in the demo, where I will just create an envelope where I will apply or evaluate a certain load train on a certain lane, which you can see here. So we'll just then drag and drop a certain lane. So this is now the first lane, the outermost lane. And I want to evaluate the tandem system 300 on it and store the results in this envelope. And that's already it. So same I do for the second lane, where I apply the second heaviest vehicle. And then finally on the third lane, I will apply the 100. And of course, they should not all be just added, right? Because let me just go back once more, because you can already imagine, of course, if for the anti-clockwise torsional moment, of course, I do not want to put this load on it because it will be favorable for it. So, of course, the user doesn't have to think in that way of it. He just superposes all the individual loads with the superposition rule and, which means the program will just check, because, of course, for the bending moment, he will only add the result if it's more unfavorable. So the last train, of course, would be added for the bending moment, but not for the torsional moments. Of course, the program checks each individual result when we apply this. So it's not like putting a load train on or not, but this is considered for each individual result component. And therefore, we have this superposition rule and, which will just edit if it's more unfavorable for the considered situation. And then this is already our final envelope for the position left. Then we will do the same for the right side, superpose them with OR, and then we have already our tandem system implemented. Okay, that's so far to the theory, but let's have now a look how this is really done in the software. So I will just change to the program, and I will show you this on our getting started example, which you can also open here in our library. And you can see the complete traffic load application in this example, also documented here in this manual. And I will just show you a part of it, like the tandem system application starting from the left side. And you can imagine that all additional things, they work exactly in the same way. So you will already understand the principle by this. So I will go to the tab Analysis, where we have our materials, our cross-section. We have already introduced our stage calculation. So I've deleted all the other stages so far that we can focus on the essential parts. So this is just the erection of our bridge, span by span. Then we apply the STL loads, and now I'd like to show you how to do the traffic load on it. For this, I move to the next tab, Traffic Loads, and you can see here two menus. One is for the definition of the lanes and the other for the load trains. So it's very easy. And to get started with the lanes, I will make a new group. So I didn't mention that before, that we organize the lanes in group just because it's for a better handling. You will see in a second the advantages of grouping the lanes. Then the program directly jumps into this window for defining the lanes, and on the bottom right corner we have our structure. Here we will define our assemblies, so to tell the program on which elements the lane should be applied, and here we will then see it in a second our cross section. We have not applied any assemblies yet, so that will be the first step. So I will click just here the tool, assembly. I will select the main girder, and now I can define from which position to which position the lane should run. If I want it over the whole structure, I just press the Enter key and quit the tool, and you see now this is my assembly where the lane is applied. So the principle works exactly the same as also for other loads. Select an assembly where you want to define the lane. And then I already get a nice preview of my cross section. And during the input, I can always switch between the 2D view and the 3D view. So some definitions are nicer to do in the 2D view. You will see this also in a second. Okay, so now we are ready to define the lanes. As we said, I want to start here from the left side with the 3-meter lanes. And I will show you first once how it is done manually. And then in a second step, I will show you how to do it automatically. This blue vertical line is actually our reference line, so which our lanes are referring to. So if I now would start to define a lane, it would refer to that line. We can also shift this afterwards. You will also see this in a minute when we then copy it. So, but I will do it right now at the beginning. So I want to move this line. So if I click the line, I have here in the context menu the offset, or you just click this tool here. It's exactly the same. To put this basic reference line to the right position. So, and now I can move it here interactively. And in order to do this very nicely, I will now switch to the 2D view. And now I have a view of my cross section with all my parametric lines. Actually not all, but only the vertical ones, because these are the lines that I need. And now I can very nicely shift this offset here to the edge of the roadway. And now this will be my reference for defining the lanes. And now I can start to define the lanes. And this is here, this first tool. As I said, now this is the manual approach. You see here, this is my reference, this is 0. And now I can either to the left or to the right side start defining a lane. So I would just move it to the right, click, and then adjust the value, 3 meters. This was already something double. Let me just double check what happened now. Maybe I clicked 2 times. Let me try again. So I will define a lane here by 3 meters. Press the Enter key. Yes, then the first lane is added. And then the second lane, to have a nicer input, it's not related to the first blue line, but I can directly have the offset from the end line of the first lane. So I could go 3 meters further, and related to this lane, another 3 meters to the right. And then I have my remaining area, because no more 3-meter lane is fitted here. And now I need to calculate, or I just go to the 2D view, and then I can simply say, okay, here where the curb ends, here this should be my width, and then I have already defined my 4th lane. Then I quit the tool, and my lanes are already defined. So even if you do it manually, you can see it's quite quick. Just before I show you the automatic approach, I will also show now how to define the lanes now very quickly from the other side. So starting with the 3-meter lane from the right side. It's easy. I would just copy the whole group. And this is the advantage of the group also. So when I copy the whole group, I will just say this is now lane set 2, for example. Then, of course, first I have exactly the same content. And then I will go to the property window of this lane set and just say mirror it. If I say mirror, the program does exactly that. Now the lanes are mirrored. Of course, the position is not right, so I will adjust here the starting reference line again as we have done before. So you can see you can also do this afterwards. Change again to the 2D view, click the wished line, and I have already my settings for the other direction. So one starting from left, one starting from right. Okay, there's also one small thing which actually has not a big effect, but just that you see that my vertical loads, they are now related here to this horizontal line. Now, if you're very accurate, and you say, no, but my cross section is inclined, I want to relate it to the inclined section. So also this is possible. We have here a function where you can align it to a certain boundary. So maybe it's even here the surface. And then you can see it's related to here. So for the vertical loads, this will not have any effects. For the longitudinal loads, it will have some more eccentricity to the center. But just that you know that you can also do that. Okay, finally, I would like to show you how to do the automatic lane definition. So for this, I will make another group, lane set 3. Of course, I again need the assembly. Just click enter. And now I'll use the tool lanes by standard. If I click that, I just need to tell the program what is the roadway width. So I said he should start from here and go to here. And you see with 2 clicks, I have exactly the same result as I've manually defined. Here I have aligned the lanes to the inclined one, so therefore there's a little difference in the display, but it's exactly the same thing. Okay, you can see here in the property window, this is also I wanted to mention what I said before in the PPT. Here you can define which direction should actually be evaluated on the load position. You see here, this is our load position. I could also move this and adjust this. So by default, it's in the center. And here you define for which direction you want to evaluate the influence line. Yes, that's it for the lanes. Now let's jump to the load trains. It's the same menu, just a different sub-menu. Also here, I will make now a new load train. And just to show you the input, I will define some arbitrary load train, starting with a single load, and then having some distance to the next load. See if it's constant, then there are just the 2 same values here. If you want to have an interval, you just change the second one. So this will then change into this interval. Then I could have some uniform load, for example, with the density of 10. And the length of this load, it's constant. Just put in the value. If it's changing, you can change the second value, and so on. I think this input is very easy, so I think I do not need to explain here any further. Just one thing I want to show you for the uniform load. Here in the property window, here you can define if it's a line load in kilonewton per meter or if it should be considered as an area load. So this is the thing here. And another thing is, okay, it's called floating length. Was just a bit puzzled by the term. So this is where you say it doesn't have a certain length, but it should have, yeah, because maybe it's more accurate to say floating length. So it's not infinite, but it's really like an adjustable length that will be done to the most unfavorable condition by the program. I will show you this also at the end of the presentation. So this is how you define the load trains. And of course, we can also load the predefined trains by Eurocode according to the particular load models. So I will just load here the tandem system. And we see immediately we have the tandem system 300, 200, and 100. And first, you cannot change them because they are from the library, but you could also convert them to generic type, and then you could also adjust these trains by a factor. Yes, that's about the load train definition. And now we are ready to go to the superposition. So I just go here to the tab below, and this is actually the tab where we, there's some remaining stuff in here, or maybe it's already put there because I've used these trains. So let me just delete this. This is also the template where you see here where you do the load case superposition for the additional loads. And just below, we have another tab, graphic loads, where we have our defined lanes. So we just pick one of the lane sets now, and our defined load trains. And before we superpose them, we need to do the evaluation, but we can do this directly here. So how do I start? I will just create an envelope, same as you do also for other load superposition. And I want to say this is now maybe my lane 1, and I want to put here the tandem system 300 on it. So let me just enlarge this a bit. So this is an envelope, and what do I want to superpose in this envelope? As I said, on the lane 1, so I just drag and drop this lane 1 into here. I want to evaluate the load train 300 or tandem system 300. So I can also expand this so that I can also see this here once more. So this is not a superposition, so therefore also the color here of this is a bit different as for the normal superposition. This is an evaluation. Yeah, so here now the load train 300 is evaluated on this influence line, and the results are then in this envelope. So in this way the user can prepare this. So in the next step, I will make then the lane 2 with the tandem system 200. This is my next envelope. And here I again simply drag and drop the respective lane and the train into it. Again, I can expand this just to check what's in there. And one final envelope for the third lane, lane 3, tandem system 100. And again, I will drag the lane 3 and the tandem system 100. So I have 3 partial results. And now finally, I want to superpose them to a final envelope. So for this, I will now make a final envelope for the tandem system. I would call it left. So I'm starting from the left side. And now we are back to the normal superposition. Now these are already envelopes. And now I will just superpose them in a common way that you already know from the other load definitions or superpositions. And now I need to take care about the rule, the superposition rule. I do not simply want to edit, but as I mentioned before, only if the considered result component gets more unfavorable, therefore I choose the end. The same I do for the second lane. Again, I need to edit the superposition rule. And finally, the third one. And again, I change to end. I can also expand this just to double check. And you see, yes, that's okay. So all the individual results are superposed with end. And here, this is my final envelope for the left side with the most unfavorable results. So you can imagine I do the same for the right side. I get exactly the same scheme, and then I will superpose the left and the right with the OR rule to get really the final result for the tandem system. One more remark before we proceed. I wanted to mention here within the lane in the property window, here you can finally say which direction you want to evaluate. You know, as we have seen before, the influence line can be evaluated for certain directions, and here you say, or calculated for certain directions, and here you say actually which line you now want to use. So therefore it's written once more here vertical. Okay, with this we almost done, and there's just one more step to calculate this. So we have prepared the scheme, the program knows everything. So I jump to my constructions and I make a new stage, not a new construction, but a new phase, sorry. Yeah, it's a new phase. I call it just traffic. This is evaluated on the final structure. So this is not a construction schedule, but so I will put this to final. that it's calculated at the end. And then I just need one task for it. And this is actually here in the group traffic loads, there's the subtree. You already know this task actually also from the normal load superposition. It's exactly the same. It's just for reason of overview. It's also once more here. We don't need the influence line calculation. This is automatically done in the background. So you only need this if you just want to evaluate an influence line that you would take this command, but otherwise we just take this subtree, evaluate the superposition from the tree. Which one? Of course, the final one. We don't need the individual ones because they will be done automatically. You will see this in a second. So just take the final one, the resulting one, and with this, the program will now do everything. He will calculate the influence line. He will evaluate all the traffic trains on the lines, and he will do the superposition. Just click the recalculation. Good, no errors. So let's have a look at the analysis, at the result menu. And I will maybe go to the 3D diagrams just to have some quick check. And here at the bottom, I go to my envelopes. And right, you see here the individual results, and you see the final envelope result. Okay, I need a new diagram. This was just the view. Yes, now it works. So this was just a view, and of course in this view I can make a series of diagrams. And now I just have to check which result component I want to see. Let's have a look at the bending moment. And now I also need to have a look at the correct line of the envelope. Maybe I'm already a bit over time. I hope you have some time left. Just maybe it's important to understand this. So when I say here superposition, I just wanted to point out once more how this envelope looks like. So unlike like a normal load case, I don't just have one single result, but of course I have the maximum and minimum forces due to each result component, right? So whenever I have a look at the result, MZ, I also need to say the program, to tell the program from which line he should take the result. Therefore, I need also to get here the min and max MZ. So let's have first the minimum. Then I will just copy this diagram and change also to the max. And then I have for each element position, I have the most unfavorable bending moment that can occur from all the different load positions that we might have. This jump here derives from the fixed pier because we have here a rigid connection. So it looks quite reasonable. So that's actually what I wanted to show you. And before I finish, maybe one more step or one more thing. As I said, the influence line, they are automatically calculated in the background, but it's nice. The user can also have a look at them to check certain behavior. So if I go again in the result menu to the influence lines, I can select a certain lane. Of course, this we haven't calculated, so I need to go to the lane we have evaluated. And you can see here for all the internal results, maybe I will also switch off some of them, just we have a nicer view at the bending moment. And now I can here simply switch through the structure, and I can see then the influence line for all the particular positions. You can also directly click on a particular element. So this would be the center. So just to point out once more what this means. So the influence lines means we're always looking now at the result at this position. At the abscissa here shows where the uniform load or where the single load is put on the structure to cause the respective moment. Like, for example, if the unit load is here in the center, this means here, the abscissa here, I get the maximum positive bending moment. It's clear. If the load is positioned here, in the middle of the first span, I get the minimum bending moment here. Okay, so that's important to understand. The influence line always refers to the position I've selected here, and the abscissor just shows the position of the unit load. So that's the way how they need to be understood. And what's also nice is I can also evaluate a certain train on it directly, so I can also see where did the program now put the tandem system. Of course, this is not surprising because the single force and the tandem system, they're almost the same. So maybe just as a last step, I really want to show you this uniform load. Let's just go once more to the analysis and change the this train. Here, I would just delete the two items before it. Now we have here this like infinite load, which says put it in the most unfavorable position. Not sure if I need to calculate, I do it. And then I go back to the results once more. So I pick one lane, so it doesn't matter, first or second. And I want to have a look again at the influence lines. And now I want to evaluate it with this uniform load. It was the load train 1. Now we can see that's more interesting. Now it can also be understood very nicely how this works. So again, I'm looking at this load result here at the bending moment, and I can see in order to get the most unfavorable or the biggest bending moment, the positive bending moment at this position, the load is only placed here in midspan. Okay, so exactly between the piers, which is reasonable. But to get the most unfavorable or smallest negative or biggest negative bending moment, the uniform load has been placed here on the left span and on the right span, because then I get some upwards deflection. So I think in this way, you can see that the program really very carefully analyzes all the possible positions and how this works in the program. So therefore, I hope I could show you simple. Yes, of course, behind it's quite complex, but I think the input is still quite simple, and you can see it's also very accurate. So in that sense, I think I have shown you in this short time how this is implemented, and I hope you got an impression how it works and that you can now also carry it through in your projects. So with this, I'm already at the end of my presentation. I hope you liked it. If you have any question, you can still get back to us, our support address. Just go here in the program and contact our support. And also in the next year, we will have some nice webinar series. So we will start in January with our new parametric prism free form modeling and all the Boolean operations that we have there. And then there will be another series also based on analysis. So stay tuned. Of course, we will inform you, and hope to see you again next year. Until then, thank you for joining and watching, and have a nice day. Thank you. Bye-bye.